Okay, so in this class, we are going to cover, on the wrong page. In this class, we are going to cover all of lesson 16, and then we'll start lesson 17. So lesson 16 is right down here. It's called Working with Radicals. So we'll do that, and then all the activity stuff, and then we'll come back together and do the demo for lesson 17, which is roots and radicals. So the last two classes have been focused on exponents. It's been maybe a week since you've thought about exponents because we had the test in between. But now we transition from exponents to radicals. Turns out it's a very natural transition from a certain perspective. So that's the plan for today. And we'll come up here at the start of lesson 16. In this lesson, we simplify expressions that contain radicals. Oh, I think I have something to hand out to you guys. Did I give you this? Oh, all right. So let's hand these out. Just take one and we'll pass them all the way around. So the thing I'm handing out now is something that doesn't exist in the packet. On the first page of this new packet, there's a chart with 5 rules at the bottom. So this handout here has those 5 rules plus some other ones that we're going to cover today in the next class. So it's not something you'll have with you on the test, but it is something that you can use during homeworks, and so you don't have to keep flipping back to find these rules which are buried in the packet. Okay, in this lesson, we simplify expressions that contain radicals. The rules of radicals are going to come fast and furious in this lesson, so hold on to your hats. Number 1, there are 2 numbers that when you square them, give you 25. What are they? Five is one of them, because 5 times 5 is 25. What's the other one? Negative 5, because negative 5 times negative 5 is also positive 25. Yep. So there are 2 numbers that when you square them, you get 25. In general, all positive numbers have how many square roots? 2 of them. Right? Any positive number like 25 has 2 numbers that when you square will give you the original. One of them is always positive. One of them is negative. Now this is a symbol that you have seen before. What's the name of that symbol? Or how would you say that thing out loud? Square root of 25 is what we would say. Yes? Okay. Oh, I can fix that. Anybody else not have a packet? Sure. Okay, so that symbol is one, you're welcome. So that symbol is one that you've seen before, and you would say square root of 25 or radical 25, right? Words that you've seen before. When we give you this symbol, we don't mean both 5 and negative 5. We mean the positive answer. And so the square root of 25 equals just plain old 5 when it's written in that form, okay? Even though there are 2 numbers that when you square them give you 25, when you see that particular symbol, like the check mark symbol, the radical sign, we're talking about the positive one. So it only means the positive one or the principal one. That's what we call it, even though there are 2 numbers that in theory would give you the 25, okay? All right, so some square root vocabulary. The word radicand is the thing inside the radical. The index is this little number that goes out there. And then the radical sign is that check mark looking symbol, okay? So just some vocabulary. When we talk about the index, I've got a little magic number up there. Let's talk about this next one, and then we'll figure out why there's no number in front of that square root 25. So this problem right here, how would you read that with the 64? Cube root of 64, meaning what number times itself 3 copies will give you 64. What is that magic number? It's 4. And if that isn't something familiar to you, you've got this reference sheet that we handed out last time. If we're looking for the cube root of 64, where will we find it on this reference sheet? You have one of these? Have one of these? Yeah. Okay, where are we going to find the cube root of 64 on this reference sheet? Under perfect cubes, because we want a number cubed to give me 64. So we look in the perfect cubes column, and we're looking for the magic number 64, and we find it, and then we go all the way to the left, and what number do we see? 4. Everybody understand? You guys are looking at me. I need you to look at this document because this is what's going to help you on the homework and on the quest. You see it? Find the number 64 in the perfect cubes column. Tells you 4. Now, some of you, you just have this fact. It's just memorized for you. But if I asked you, for example, for the 4th root of 625, I'm assuming you don't have that memorized. 4th root of 625, can you find it on the table here? It is 5. Yes? Okay. And I think I mentioned this before, but the upcoming quest is non-calculator, and so you're going to make sure you know how to use this thing to answer problems like that, because you won't have the calculator to type into. Okay, so that's fine. Again, what's the vocabulary word for that little 4 and that little 3? That's the index. Now, when we talked about the square root of 25, we didn't see a little number written up there. What is it? It's invisible, but there's a number that should be there. 2. Because we were looking for a number like 5, so that 5 times 5, 2 copies of that number give you the 25. 3 copies of the 4, 4 times 4 times 4, give you the 64. So there is an invisible 2, but because the square root is so common, we just decide we're going to be a little bit lazy, and we'll all agree, hey, if we don't write a number in front there, we're assuming it's a 2, okay? And that's not very uncommon, actually. You guys do this all the time. What is that? Say that out loud. X cubed, say this. What's this? To the what? The first. Do we write a 1 up there? Do we want to write a 1 every time we put something to the first power? No, it's the same idea. It's really just us being, I don't know, you choose the word lazy or efficient. Either way, it's just a choice, okay? So there is an invisible 2 on those square roots. Okay, number 4 talks about the cube root of 64 is 4. We've seen that already. I'm going to write 64 as 4 cubed. This is something that's true, right? 64 is the same as 4 times 4 times 4. And so if you see the cube root of 4 cubed, then in some sense, maybe you can recognize that the cube root, including that radical sign, is exactly opposite of cubing something. And so they literally cancel, and you're just left with the 4 that was inside. We buy that? And so same idea over here. If you see the cube root of x cubed, the cube root and cubing are opposites of each other. And so what's the answer when we simplify that thing? It's just x, okay? And so this is something that we're going to take advantage of, like in number 5, 4th root of x to the 4th. What does that equal to? It's x. And we can give you crazy complicated things, but if you understand this principle, then your life will be good. 3 plus x squared over 5 to the 17. We can simplify this. What is it? It's 3 plus x squared over 5, because the 17th root and the 17th power are opposites, and they just plain cancel. So we're left with just the stuff in the parentheses. Okay, everybody understand that idea? Okay, number 6 talks about simplifying the cube root of x to the 21st. So it's written out there, but let's give ourselves something to do here. We'll be a little bit active. So can you guys find some space here? And just copy the original. Cube root of x to the 21st. And then write that with some blank parentheses in there. Would you guys agree that if we could somehow rewrite x to the 21st as something to the 3rd, then this problem would be easy? The answer to this problem would just be whatever's in the parentheses. By that? Same as the 17 and the 17. So we're going to go out of our way to force x to the 21st to be written as something to the 3rd. Okay, so let's fill in the something here. It's definitely going to be x to a power. I'm going to put a little blank box up there. What's our rule for how to handle these exponents? They multiply. That's one of our rules from before, yeah? So what magic number are we putting in the box so that we still have the 21 x's that we had before? 7. So put a 7 right there. It's still x to the 21st, but it's written in a much more useful form. And then, like we said, cube root and cube are opposites and they cancel. So what's the answer to this? This is x to the 7. Okay, that's it. Now, some of you may recognize that there's a shortcut going on. What can we do with the 21, the power, and the 3, the index, to get the 7 is the answer? Because we divide, right? 21 divided by 3 is 7, and that works, and that's legitimate. It's exactly what we're doing. Don't do that. Right now, we're just building intuition. I don't need you to memorize some other random rule. There's already enough of those floating around at the moment. We'll have that shortcut soon enough, but for today at least, let's just do this basic idea. Let's try here x to the 20th, the 4th root of that. 4th root. What power would I really like to put up there? 4th power. If I can get those to match, then they'll cancel. So can you copy that part down and fill in the blank? What's the magic power that will keep us with the 20x's? It's 5. Everybody see that? Yes. Yeah, on the quest coming up, by the time we get to the quest, we'll have the shortcut, and I don't need to see this intermediate step. But for right now, we're just developing our intuition. What's the answer here? X to the 5th, right? 4th root, 4th power, cancel. Same idea for part B, although this one, there's a 64 in the way, but that's okay. Again, what power would I love to put up here? I'd love to put a 3, so put a 3. Okay, the x's, I had 27 of them. What am I putting here? 9, because I know I'm supposed to multiply the 3 and the 9. Okay, that's good. What about the 64? It's 4, isn't it? Because 4 cubed is 64. So 64 has now been rewritten in a nice form. It's 4 cubed. So then again, stuff cancels. And what's our answer? 4x to the 9. That's it. Any questions so far? Okay. Number 9 asks us to find the value of 2 different radical expressions. So the first one is a square root of 9 times 4, and the second one is square root of 9 times square root of 4. Let's tackle the first one first. This is the square root of what number? 36, right? And the square root of 36 is 6. So far, so good. Over here, it says do the square roots first and then multiply at the end. Square root of 9, 3 times 2 is 6. And it was the same answer both times, right? 6. And so it turns out this is true in general. If you have the square root of 2 things multiplied together, you can multiply first and do the square root last, or you can do the square roots first and multiply last, and you get exactly the same answer. And that's written out here in number 10. If you have a times b underneath the radical, you could do the radicals separately, multiply at the end. It turns out division works just as nicely. If you have a fraction inside of a radical, you could do the fraction first and then the radical, or you could do the radicals first and then the fraction. Either way, we'll get the same answer. So 2 brand new properties. They are on the sheet that we handed out today. Next page is going to be our first opportunity to use one of those 2 new properties. Okay, we're going to simplify the cube root of 16x to the 4 times the cube root of 2x to the 19 with a warning that says this will be tough. It will be. Okay, first of all, this is 2 radicals with what symbol in between? Multiply. And that's one of the nice things that we just saw on the previous page. So we can push these guys together and make one single radical. And that one single radical is written right there. Okay? Used to be written, do the radicals first, then multiply last. Now it's written, multiply first, do the radicals last. hopefully we buy that they're the same. Okay, then we're going to do this multiplication. 16 times 2 is 32. What do I do with the powers? X to the 4 and x to the 19. We add them. That's one of our old properties now. So we get x to the 23. So 32x to the 23. The reason that we like to push the two radicals together before we do anything is that we've made it simpler, right? There used to be two separate radicals. Now it's one single radical. So even if the rest of this is tough, at least we're only doing the tough thing once, as opposed to doing it with the two originals. Okay, so here's the hard part. And I know the answer is written there, but we're just gonna write it here. So you got some blank space. Here's what I want you guys to do. I want you to write 2 blank cube roots with a multiply sign in between. Okay, the first thing I see is 32. The cube root of 32. Is that something nice? It isn't. And if you happen to know your small perfect cubes, you just recognize 32 isn't one of them. But even if you don't, you got that reference sheet. You look in the perfect cubes and you'll find 32 is not in the list. But what we can do is find a number that is in the list that goes into 32. So we're looking for factors of 32, but not any old factors, only factors that are in my perfect cubes list. 9 is, yeah. Yeah, so 2 goes in 16 times, right? But is 2 in my perfect cubes list? No, is 16 in my perfect cubes list? Yeah, 16 is not in my list, not in the cubes list. So even though 32 factors into 16 times 2, it's not helpful to us. So it's not just any old factoring, it's only the perfect cubes that we care about. You guys have your reference sheet. We also have the perfect cubes in green over here. I don't know how much of this you guys can see, but for example, 12 cubed is 1,728. So I'm looking in the bottom row for a number that goes evenly into 32. Do you see it? 8 goes in to 32, yeah? So what we're going to do is we're going to rewrite that 32 as 8 times whatever is left. 8 times what will give me the 32? 4. Okay, so it's still 32, it's just written in a different way. Next step, we're going to take those x to the 23, and we're going to try to write them in a nice way. This is a problem I'm just going to do part of up here. Cube root of x to the 23. Cube root. I'd really like what power? Really like a 3. Can you take that 23 and break it up into something to the third? Yeah, but is there a number I can put in there that's going to work? 7. 7 times 3 is 21. So can I put 7 there?
Yes. Can't do anything.
But can I put 7 and still have it be the 23?
No.
No, we can't make 23. So we say, okay, 23 is no good. We can't deal with 23. What if I peel one of those x's off? It's not really clear why I could do this, but we'll do it in just a second. But I have 23 x's. I can't use all of them. Let's try taking one of them away and dealing with 22. Can I deal with 22 of them? No, because I can't make 22 something times 3. So that didn't work. Let's keep peeling off. Can I make this work? We can. What's the magic power here? Is 7. And so what we recognize is that 21 of those x's are useful, and the rest of them are just going to be left over. So in the same way we took 32 and broke it into a perfect cube, 8 times whatever was left, 4, we're taking our 23 x's and we are breaking apart. How many of them are helpful to us? 21 of them are helpful. And then how many are left over here? 2 of them are left. And when we do the next step, you'll see why this is a good way to break up the original radicand. Okay, so I'm going to go up here and run out of space a little bit. Again, I'd really like this to be something cubed, yeah? 8 is what number cubed? 2 cubed. X to the 21 is going to get rewritten as x to the what cubed? 7. And by that, I'm going to copy this other guy. Cube root of 4x squared is just going to hang out and be in the final answer. So we took all of the good stuff. We forced it into the first radical, and then we wrote it all as a perfect cube. So we can take advantage of that nice property that says cube root and cube are opposite and they cancel. And so what does this first radical become? Just 2x to the 7, because the cube root and the cube are opposite. And so our final answer is just 2x to the 7 times the cube root of 4x squared. That's written down here at the bottom. 2x to the 7 cube root of 4x squared. That is tough. You will have practice with the easier ones first, and then you'll build up to harder ones like that, but that's tough. Okay, moving on to number 12. It says find the value of the following radical expressions: square root of 9 plus 4, square root of 9 plus square root of 4. On the previous page, we saw the same kind of thing, but instead of plus, it was what? Multiply. And we got the same answer, whether we multiplied first or last, yes? So let's see if addition works as nicely as multiplication. The first one is really the square root of 13, which is approximately, how much? Oh, that's 13 squared. I want to go the other direction. Yeah, so 3 point something. Yeah, it's 3 and change. Over on this side, square root of 9 is 3 plus 2 is 5. Are they the same? So despite how much we might be tempted to look at the square root of 9 plus 4 and say, oh, that's just the square root of 9 plus the square root of 4, it isn't. And so that nice property we had with multiplication and also with division simply does not work for addition or subtraction. So very important, if you see a radical of the form x plus y or x minus y, we can't do anything with it. Cannot be simplified. In particular, this is one of the most common things folks like to do, is say that the square root of a squared plus b squared is really a plus b by taking that square root, like in a sense distributing the square root over the addition. Looks promising, but it's just wrong. Let's see, so not equals, put some more, like take out your frustration, whatever you're mad at right now, just cross that off, like lots, cross it off lots of times. It's really, really, really not true. Okay. All right, so I think the last piece of new stuff in this section has to do with adding and subtracting radicals. So it says we can, this is 14, it says we can add and subtract radicals if they are like radicals. Radicals are like only if they have the same radicand and the same index. That's a lot of vocabulary. Let's look at some specific examples. 5 square root of 7 plus 3 square root of 7. Those guys are like radicals because they both have a 7 inside. What's the index, even though it's invisible? Is 2, right? We all agree that invisible is 2. So because they have exactly the same index and the same radicand, they're like radicals and we can combine them. It doesn't bother me that the 5 and the 3 are different. They're outside. It's just the radical itself. So I just think of this as counting. I have 5 apples and I'm adding another 3 apples. What do you have? 8 what? Apples, right? And so in this case, we just get 8 apples, 8 radical 7. Notice that the 7 doesn't become a 14 or a 49 or anything other than 7. And this problem is really no different than 5x plus 3x. What is that? It is 8x. You guys are not tempted to mess around with the x. Just because it's a radical 7 doesn't mean you should be tempted to mess around with it. It stays exactly as it is. So, tougher problem is like the one that's written out here. We'll just run through it real quick. All right, so I'll highlight the original. It's this. Square root of 12 minus 2 square root of 75 plus 7 square root of 27. How many radicals do we see? I see 3. Do you see 3? Three radicals. Are any of those three radicals like radicals? No. They all have the same index, right, because they're all square roots, but the thing inside, which is our fancy word radicand, are different. You can't add them, not in their current form. But if we do a little bit of work, we actually can. Would you guys agree that square root of 12 is the same as square root of 4 times 3? And that the square root of 4 times 3 is the same as square root of 4 times square root of 3? Multiplication inside works perfectly nicely. This was our nice multiplication property of radicals from the bottom of the previous page. So that property works for multiplication, works for division, does not work for addition and subtraction. Okay, and then the square root of 4 is nice. That's just 2. And so I'm just circling things that are equal. So that's 2 times square root of 3. Yeah? So that's how we simplify a single radical. We actually did it up above in a much more complicated example. But 12 became 4 times 3, which got split up, and the 4 came outside of the radical as a 2. It's the same idea for the next one, so let's keep circling here. 2 radical 75. We're going to take that 75, which is not a perfect square, and we're going to factor it. We need a number that is a perfect square that goes into 75. What perfect square goes into 75? It's 25, right? And so we're just running down. We have the perfect squares in yellow here. Just looking at these bottom numbers, our perfect squares, and asking, do any of these go into 75? Does 4 go into 75? No. Does 9 go into 75? No. 16? No. 25? Yes. And 75 is just 25 times 3. So we still have 75, but now it's written in a more useful form. And then I can split apart that 25 and the 3 like that. Square root of 25 is 5. That's why we did it. That's why we factored it this way. So that comes down there. And the only new piece on this one is that there was a 2 in the front of this radical 75 the whole time. And so when people have the 2 on the outside and then the square root of 25 came out as a 5, sometimes people aren't sure what to do with the 2 and the 5 and they add them. But it's multiplication because it's been multiplication this whole time. We didn't write it, but that's really 2 times. In the same way it's 5 times x, right? So we didn't put a symbol there, we mean multiply. So that 5 comes outside and multiplies by the 2 and becomes a 10, radical 3. So that's there. And then I'm going to circle in purple again that 2 radical 3. And now what can you say about purple and green? What kind of radicals are they now? They are like radicals, and so we can push them together. So the moral of the story, sometimes you have radicals that they appear to be unlike in the beginning, but if you simplify them using some new techniques from today, you can turn them into like radicals. So I'll just circle in blue this guy. We won't run through the calculation, but it turns out 7 root 27 is the same as 21 root 3. And now I have 3 like radicals. So we're just carefully counting how many we have. 2 of them, minus 10 of them, plus 21 of them. Is that 13? I count 13 of those. Is that right? Is that okay? 2 minus 10 is negative 8. Plus the 21 is 13. So our final answer there is 13 radical 3. Any questions on that? Okay, so there's a lot going on in this section. I gave you a little bit of a warning about that at the start. So we're going to take our time going through the activity. We are going to do the demo from the next class later, but let's see how far we can get in the activity here. And take your time as you work through this new material.